All right, welcome to the Physics Chapter 2 Extra Practice Problems 1 through 5 Solutions. These are on page 565. I went ahead and put our three equations from this chapter up at the top. And so let's go through these. So number one says a physics student drops a rock from a 55-meter cliff. How long does it take to hit the ground? All right, let's just go ahead and write down what we know. So we know that delta x is negative 55 meters. So make sure you make it negative. It's going down. That's an easy thing to mess up. Acceleration, we're in meters, so it's negative 9.8 meters per second squared. We want to know how long does it take to hit the ground. So we want to know time. And we know the initial velocity, since it wasn't thrown down, it was just dropped, is equal to 0. So we're looking for time. We need an equation that has time in it and delta x, and that's going to be equation number 3. So I have delta x is equal to v naught t plus 1/2 at squared. This will be 0 since initial velocity is 0. So I'd have negative 55 meters is equal to 1/2 times negative 9.8 meters per second squared times time squared. So time squared is going to be negative 55 meters divided by 1/2 times negative 9.8 meters per second squared. Right, time squared is 11.2 seconds squared. So let's take the square root of that, and you'll get a time of 3.35 seconds. All right, great. So that is number one. Let's see if I can squish number 2 in here. So number 2 says, how far will a car travel while it accelerates for 3.2 seconds at a rate of 2.5 meters per second squared? Prior to the acceleration, the car was traveling at 9.8 meters per second. All right, in this case, so let's just write down what we know. We know that time is 3.2 seconds. Acceleration is 2.5 meters per second squared. We have an initial velocity of 9.8 meters per second. And we want to know how far, so that is displacement. So we need an equation that has both time and displacement in it, and that once again is going to be equation 3. Okay, so let's just fill in the numbers here. To equation 3, we would have delta x, what we're solving for, is equal to initial velocity 9.8 meters per second times time 3.2 seconds plus 1/2 times 2.5 meters per second squared times 3.2 seconds all squared. All right, so delta x, if you do them separately, you certainly don't have to do that, but in case you missed it, I'm going to go ahead and write down these numbers. 31.36 would be the left side, and then the right side would be 12.8. So add those two together at 44.16 meters. So not a hard problem. What I see all the time students mess up with is they forget to square the time in the second part of that equation. All right. Let me erase this for a second. We'll do 3, 4, and 5. Okay, number 3 says, how long does it take a bullet to accelerate from rest to 3,050 feet per second at a rate of 2.96 times 10 to the 5th feet per second squared? All right. How long? So we want to know time. Okay, at rest, our initial velocity is going to be 0. Final velocity is 3,050 feet per second. And acceleration, got a big number, 2.96 times 10 to the 5th feet per second squared. Okay, we're trying to get time. We know initial velocity, final velocity, acceleration. I think we can just put this into equation number 1. So I'd have 3,050 feet per second is equal to 0 plus 2.96 times 10 to the 5th feet per second squared times time. So time is going to be 3,050 feet per second divided by 2.96 times 10 to the 5th feet per second squared. All right, so just to make sure, since in case you've not been doing a ton of scientific notation, looks like I need to charge my calculator up. So this would be 3,050 divided by, I'm going to put a left parenthesis, 2.96, second function double E, 5. All right, so that e to the 5th, so 10 to the 5th, right parenthesis, and you will get 0.0103 seconds. So it doesn't take very long, but you know, it is a bullet. All right, let's see if we can squeeze number 4 in here. Number 4 says, an airplane accelerates at negative 3.1 meters per second squared down a 3.8 kilometer runway. What is the fastest speed with which the pilot could land in order to assure the airplane will stop before reaching the end of the runway? Okay. Well, what is the fastest speed with which it can land? So what is that? I'll give you a second to tell me what it is, or at least speak it to yourself. All right. That's the initial velocity. That's what we're solving for, the speed with which the plane can land. What would our final velocity be? Well, it's an airplane and a runway. We hope it's 0, so the thing can get stopped. Delta X, we have to be careful here. They gave it to us in kilometers, so we got to change that to meters. It's going to be 3,800 meters. All right, so, and what else do we know? We know acceleration, negative 3.1 meters per second squared. Okay, no time is involved here. We want to know initial velocity, so it looks like we're using equation 2 here. Final velocity squared is equal to initial velocity squared plus 2 times acceleration times delta x. All right, so that's going to be 0 squared, or just 0, is equal to v naught squared, it's what we're trying to get, plus 2 times negative 3.1 times 3,800 meters. All right, so let's see, if you multiply that out, 2 times negative 3.1 times 3,800, you'll get negative 23,560, but if we move that over to the left, you're going to end up having v naught squared is equal to 23,560 meters squared per second squared. So take the square root of that. Again, I like to just raise it to the 0.5 power. And that is 153.5 meters per second. All right, so number 4 is down. Let's do number 5, and that'll finish up this video. All right, number 5 says a train slows as it approaches a curve. What is the acceleration of the train if its velocity was 62 miles per hour and the brakes are applied for 12 seconds over a displacement of 8 times 10 to the second feet? All right, so I see we're going to have to make a conversion here. We want to know acceleration. We know time is 12 seconds. You want to always write all this out on a test to get partial credit. Displacement is 800 feet. And we know that the initial velocity is 62 miles an hour. Okay, so first of all, let's take that 62 miles an hour and get it into feet per second, because time is in seconds, displacement is in feet. All right, so we use the factor label method, 62 miles per hour, so just 1 hour. We want to get feet per second, so let's put feet on the top, miles on the bottom. That'll get rid of miles. Mile is bigger, so put the 1 by it, and there's 5,280 feet in a mile. That's a number you need to know. 5,280 feet in a mile. All right, and now we are going to go to, we need seconds. We need feet per second, so we'll put seconds on bottom and hours on top. We want to get rid of hours. So now my miles cancel, hours cancel, and what's left is feet per second. Hours bigger, 3,600 seconds in an hour. So 62 times 5280 divided by 3,600, that's 90.9 feet per second. Okay, so we had to do a little pre-work there to get our initial velocity. So this is an equation where we have time and displacement. That's going to be equation 3. So delta x is equal to v naught t plus 1/2 a t squared, and we're going to be solving for a here. So I've got 800 feet is equal to 90.9 times 12 seconds plus 1/2 times acceleration times 12 seconds all squared. All right, 800 feet. If you put this in your calculator, it's going to be 1,090.8. And plus 72 seconds squared times a. So 144 times 1/2. All right, so acceleration is going to be, we're going to move this 1,090.8 over to the left, right? So that'd make it, so I'll just do it like this, 800 feet minus 1,090.8 feet, right? When I move that 1,090.8 to the left, and then divided by 72 seconds squared. So you end up with a numerator of negative 290.8. That is a 7. So that's negative 4.04 feet per second squared. So we know it is decelerating, slows down as it approaches a curve. So it makes sense that the acceleration number would be negative. All right, that does it for the first half of the extra practice problems. And I will work the second half for you next video.